Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine generalized constants A, B, C and D for a three-phase medium length transmission line based on its nominal pi equivalent circuit when line parameters are given. We shall also learn how to compute percentage voltage regulation and efficiency of transmission of this line using those constants when load details are given. A 100 km long three-phase transmission line has the following data. Resistance per kilometer per phase equals to 0.1 ohm. Inductive reactance per kilometer per phase equals to 0.5 ohm and capacitive susceptance per kilometer per phase equals to 10 micromho. If the line supplies a load of 20 megawatts at 0.9 power factor lagging at 66 kilovolts at the receiving end, using nominal pi method and neglecting ligands, we have to determine the percentage voltage regulation and the efficiency of transmission. Let us now write down the given data. Power delivered to the load PL equals to 20 megawatts, that is equal to 20 into 10 to the power 6 watts. Line to line receiving end voltage VR line equals to 66 kilovolts, that is equal to 66,000 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 66,000 divided by root 3, that gives us 38,105 volts. Given load power factor cos phi L equals to 0.9 lagging. Let us now determine power factor angle. Phi L equals to cos inverse 0.9, that is equal to 25.842 degree. Expression for power delivered to the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 20 into 10 to the power 6 divided by root 3 into 66,000 into 0.9. That gives us 194.394 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 194.394 ampere at an angle minus 25.842 degree. In this case, load current IL equals to receiving end current IR. Given length of the transmission line D equals to 100 kilometers, resistance per kilometer per phase R1 equals to 0.1 ohm, inductive reactance per kilometer per phase XL1 equals to 0.5 ohm and capacitive susceptance per kilometer per phase BC1 equals to 10 micromho. Let us now calculate resistance per phase R equals to R1 into D. Using values we get 0.1 into 100, that gives us 10 ohm. Inductive reactance per phase XL equals to XL1 into D. Using values we get 0.5 into 100, that gives us 50 ohm. and capacitive susceptance per phase BC equals to BC1 into D. Using values we get 10 into 100, that gives us 1000 micromole, or 10 into 10 to the power minus 4 mole. Now we shall determine series impedance per phase of the transmission line. Z equals to R plus JXL, that is equal to 10 plus J times 50 ohm. This may be written in polar form as 50.99 ohm at an angle 78.69 degree. Shunt admittance per phase Y equals to J times BC, that is equal to 0 plus J times 10 into 10 to the power minus 4 mho. This may be written in polar form as 10 into 10 to the power minus 4 mho at an angle 90 degree. We have determined series impedance per phase of the transmission line Z equals to 50.99 ohm at an angle 78.69 degree, and shunt admittance per phase Y equals to 10 into 10 to the power minus 4 mho at an angle 90 degree. Let us now determine Y into Z. Using values we get 10 into 10 to the power minus 4 at an angle 90 degree into 50.99 at an angle 78.69 degree, that gives us 0.05099 at an angle 168.69 degree. This may be written in Cartesian form as minus 0.05 plus J times 0.01. Now we shall determine 1 plus 1/4 of Y into Z, that is equal to 0.9875 plus J times 0.0025. This may be written in polar form as 0.9875 at an angle 0.145 degree. For pi equivalent circuit, A equals to D equals to 1 plus half of Y into Z, that is equal to 0.975 plus J times 0.005. This may be written in polar form as 0.975013 at an angle 0.2938 degree. B equals to Z, that is equal to 50.99 ohm at an angle 78.69 degree, and C equals to Y into 1 plus 1/4 of Y into Z. Using values we get 10 into 10 to the power minus 4 at an angle 90 degree into 0.9875 at an angle 0.145 degree. That gives us 9.875 into 10 to the power minus 4 mho at an angle 90.145 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 38,105 volts at an angle 0 degree. We have computed receiving end current IR equals to 194.394 ampere at an angle minus 25.842 degree, and generalized constants for pi equivalent circuit A equals to D equals to 0.975013 at an angle 0.2938 degree. B equals to 50.99 ohm at an angle 78.69 degree, and C equals to 9.875 into 10 to the power minus 4 mho at an angle 90.145 degree. Expression for sending end voltage per phase Vs equals to A times VR plus B times IR. Using values we get 0.975013 at an angle 0.2938 degree into 38,105 at an angle 0 degree plus 50.99 at an angle 78.69 degree into 194.394 at an angle minus 25.842 degree. That gives us 43,138.643 plus J times 8,090.8527 volt. This may be written in polar form as 43,890.824 volt at an angle 10.62668 degree. Expression for sending end current per phase Is equals to C times VR plus D times IR. Using values we get 9.875 into 10 to the power minus 4 at an angle 90.145 degree into 38,105 at an angle 0 degree plus 0.975013 at an angle 0.2938 degree into 194.394 at an angle minus 25.842 degree. That gives us 170.90913 minus J times 44.13203 ampere. This may be written in polar form as 176.59 ampere at an angle minus 14.57285 degree. On no load, receiving end current IR equals to 0. Therefore, receiving end voltage per phase VRO equals to Vs divided by A. Using values we get 43,890.824 at an angle 10.62268 degree divided by 0.975013 at an angle 0.2938 degree. That gives us 45,015.63 volt at an angle 10.33 degree. Let us now determine voltage regulation, that is equal to VRO minus VR divided by VR. Using values we get 45,015.63 minus 38,105 divided by 38,105. That gives us 0.1814 per unit or 18.14%. We have computed sending end voltage per phase Vs equals to Vs at an angle delta equals to 43,890.824 volt at an angle 10.62268 degree, and sending end current per phase Is equals to Is at an angle minus phi 1 equals to 176.59 ampere at an angle minus 14.57285 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 43,890.824, which is approximately equal to 76.021 into 10 to the power 3 volts or 76.021 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 10.62268 degree plus 14.57285 degree. That gives us 25.19553 degree. Let us now calculate sending end power factor. cos phi s equals to cos of 25.19553 degree. That gives us 0.90486 lagging. Now we shall calculate sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 43,890.824 into 176.59 into 0.90486, which is approximately equal to 21.04 into 10 to the power 6 watts or 21.04 megawatt. Now we shall compute efficiency of transmission. Eta T equals to PL divided by PS. Given power delivered to the load, PL equals to 20 megawatts. Therefore, eta T equals to 20 divided by 21.04. That gives us 0.95 per unit or 95%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine generalized constants A, B, C and D of a three-phase line based on its nominal pi equivalent circuit when transmission line parameters are given. We have also learned how to compute percentage voltage regulation and efficiency of transmission of this line using those constants when load details are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.